So number 45, a solution containing 1.63 grams of barium chloride is added to the solution containing 2.40 grams of sodium chromate. I wouldn't give you the formula for chromate. I'd expect you to know what the formula is, which is a little more generous there. So this is a metabolism reaction, so we have to predict the product to balance it. But anyway, we're given two. If we're given the quantities of two or more reactants in this limiting reagent, the limiting reagent problem, we got to use the smaller amount method. And they want to know what the theoretical yield is, what the limiting reagent is, what the excess reagent is, and the mass of excess reagent required. Again, if I look at this problem, this is CO2 plus potassium hydroxide. Carbon dioxide can be removed from the air by reaction with potassium hydroxide. This is a Lewis acid-base reaction here. So CO2 is converted into potassium carbonate here. 15.6 grams of carbon dioxide reacts with 43.0 grams of potassium hydroxide. So we're given the amounts of two or more. So limiting reagent problem. We'll just follow the method that we did for the other limiting reagent problems. The smaller amount method. Let's see what they use here. Did they use the smaller amount method? Yeah. So going back to the barium chloride sodium chromate, they calculate yield of barium chromate from the barium chloride, 1.98 grams. They calculate yield of barium chromate from the sodium chromate, 3.75. So here, the smaller amount is 1.98, so this is a theoretical yield. We're going to use up all our barium chloride, but not all the sodium chromate. Sodium chromate's excess. So how much sodium chromate do we actually need? And that's what they're calculating here. How much sodium chromate do we actually use, or the amount consumed by the limiting reagent? So we start with the limiting reagent. We calculate how many grams of sodium chromate. So we use 1.27. If we only use 1.27, we start off with 2.40. That means 1.13 grams will be left over, unused. So this is the exact same calculation we did in class the other day. And so that would be the exact same calculation as number 46, which is the exact same calculation as number 47. Number 47 is another limiting reagent problem. Here, we're given sodium iodate and sodium hydrogen sulfide. The sodium iodate and sodium hydrogen sulfide. So we do the smaller amount. Calculate the yield from sodium iodate. Yield is 3.85 grams of iodine, kilograms. Calculate the yield of sodium from sodium hydrogen sulfide, which is 3.58. So the smaller amount will be this. So the smaller amount of product is formed from the limiting reagent here. So all the limiting reagent will be consumed, but not all the sodium iodate, which is the excess reagent, will be consumed. So how much sodium iodate is consumed is based on the limiting reagent. So we take the limiting reagent, 7.33 kilograms of sodium hydrogen sulfide, and then calculate how many kilograms of sodium iodate are required to react with that. And then we compare the initial amount, 6.00 kilograms, minus 5.58 kilograms is the amount that's consumed by the limiting reagent. So the exact same calculation as the previous one. Look back. So 48 is the same deal. Carbon monoxide is burned with carbon dioxide. 12.6 grams of carbon monoxide, 5.22 grams of oxygen. So, it can again be a limiting reagent problem. We use the smaller amount method. Number 49, same thing. Phosphorus and sulfur, smaller amount method. So for matches. Number 50, same thing. 135 grams of sodium carbonate, 188 grams of nitric acid. Smaller amount method. Basically the same calculation. Actually, let's look at the smaller amount here. Let's look at this one. you can see it's the same process. Calculate the yield from phosphorus, 236 grams. Calculate the yield from sulfur, 280 grams. So which one's the smaller amount of product? 236. Therefore, this is the limiting reagent. 236 is the theoretical yield. This is the excess reagent. Then we calculate how much of the excess reagent is required by the limiting reagent. So we start off with the limiting reagent here, 133 grams of phosphorus, and then calculate how much of the excess reagent is required. Only 103 grams of the excess reagent is required, but we started with 126. So we started with 126, only 103 grams are required. That leaves us with 23 grams of extra that was unused. Exact same calculation in all these. Okay, then we move on here. These are just conceptual review problems. There's joule, kilojoules, etc. Some energy calculations. Energy is transferred from sunlight in the photosynthesis reaction in which carbon dioxide and water combine to produce sugar and release oxygen. The amount of energy is 2.82 times 10 to the third kilojoules per mole of sugar formed. So they just want us to write the equations for this. This is endothermic or exothermic? It's endothermic. So there are two ways of representing endothermic reaction. One way is we could just put energy into the equation here. So it's CO2 combining with water to form sugar and oxygen. This is photosynthesis. So we're going to need this much energy here. Since energy is being consumed, this is energy coming from the sun, we can write it like this. Delta H of reaction, that is, enthalpy of reaction, is equal to 2.82 times 10 to the third kilojoules. So it's positive rather than negative. For exothermic, we just add minus. When gaseous nitrogen reacts with gaseous oxygen to form nitrogen dioxide gas, 66.4 kilojoules of energy is transferred for each mole of nitrogen that reacts. Transferred. Is that exothermic or endothermic? It's not clear. That's not clear, but most combustion reactions are exothermic or endothermic? Exothermic. It's not transferred. Which way, you know? I'm assuming they must be transferred, meaning endothermic means, you know, transferred to. Exothermic means transferred from. So we don't really use the word transfer. We can talk about transfer of energy, but it's not telling us the direction. Well, anyway, this is telling us the direction, endothermic. And so if they're saying endothermic, and now we're transferring 286, then it's plus 286. Here, they don't tell us if it's endothermic or exothermic. We can't assume this is endothermic. It's probably exothermic. Well, if it's endothermic, then it's the same thing. Energy is a reactant. And so either we put it as a reactant here, yeah, or we put the delta H as positive. When ammonia and oxygen react at a temperature at which both compounds are in the gaseous state, 226 kilojoules of energy is transferred for each mole of ammonia that reacts. I don't like this, transfer. I wish that instead of saying transferred, they would just say is produced or is consumed. It's much easier. Let's move on. The reaction in an oxyacetylene torch is highly exothermic. Oh, this is good. Releasing. Releasing means exothermic. Consuming means endothermic. So here we can see that this is exothermic. It produces that much energy. So it's negative. Carbon dioxide gas reacts with hydrogen gas to form carbon monoxide gas and steam. 41.2 kilojoules of energy is transferred for each mole of carbon dioxide that reacts. So again, it's ambiguous. I don't like that. This one is not ambiguous. This one's okay. 63. We saw this reaction earlier. Quicklime, the common name for calcium oxide, is made by heating limestone, calcium carbonate, in slowly rotating kilns, which are a type of oven. The reaction says, so this is calcium carbonate. Remember we saw this earlier. Calcium carbonate requires 178 kilojoules per mole to decompose into calcium oxide plus CO2. So this is an endothermic reaction. What quantity of energy in kilojoules is required to decompose 5.80 kilograms of limestone? So here, if we have 5.8 kilograms of limestone, we go kilograms of limestone to grams of limestone, grams of limestone to moles of limestone to energy, right here. Because for every mole of calcium carbonate, we're going to require 178 kilojoules. In fact, I watched the whole documentary on this reaction. It's a pretty interesting documentary. I think it was like National Geographic or something. You know what they were talking about? This reaction, where it was important? You know, the Romans discovered this reaction. They were talking about how the Romans discovered this reaction. The Romans discovered this reaction because they had time to, they said they had time to do experiments. So one of the theories goes like this, or hypotheses or whatever, is that because food was plentiful, they had time. They weren't out hunting and they weren't out gathering all the time. So they had time to do scientific experiments. So this was a huge technological achievement because this requires a huge amount of heat. You can't just do this over a fire. This has to be done over charcoal at extreme temperature. And so this is what they're talking about, the kiln. It's a special oven. And so the Romans were able to develop this. And that led to the formation of quicklime. Well, quicklime is a key ingredient to concrete. And so all those fantastic Roman concrete architectural structures would not have been made without this reaction. So they're talking about how important this reaction is for the manufacture of concrete, where quicklime is one of the key ingredients of concrete. But here, just take a look at the stoichiometry of this. I do this. I go from kilograms to grams to moles. Actually, they're doing the same thing, but we don't need calcium carbonate. This kilogram to gram conversion works for anything. So kilograms to grams, grams to moles, moles to kilojoules, using the delta H here. Okay, let's look at number 64. What mass in grams of hydrogen has to react to transfer 71.9 kilojoules of energy from the reaction? All right, so 71.9 kilojoules. Well, you know, this one we have to do different ways. Normally that one's written like this. So we have to play with the signs sometimes. And so normally this is 2 hydrogens plus an oxygen. And this state is important, you know, because whether it's a gas, liquid, or solid makes a difference in terms of energy. Like if you have solid ice versus liquid water, you know, solid ice is a lower temperature than liquid water, lower energy. So you don't worry about those types of things. And so hydrogen, oxygen, this is going to form not liquid. This is going to form gaseous water. Now, if we form liquid water, that would be at a different energy than gaseous water. Gaseous water would be at an even higher energy. And so it makes a difference. It's going to make a difference in your delta H. The delta H is going to change. Now, is this delta H positive or negative? Negative. So delta H for this reaction is minus 484 kilojoules, as written. And so we want to relate it to the hydrogen. And so we could relate it to any of these quantities here. So what we're going to do is we're going to go 71.9 kilojoules of energy. And then the way we're going to relate it to hydrogen is this. 2 moles of hydrogen, 2 moles of H2 is going to produce 484 kilojoules. And so I'm going to change that to plus 484 kilojoules produced. So if I, they say transfer, but if I produce 71.9 kilojoules, how many moles of hydrogen? This many moles. And then I'm going to go to grams. Since I'm dealing with H2, I'm not going to do 2 times 101. That's only going to give me 3 sig figs. So rather than doing that, I'm going to do 2 times 1008, which should give me 4 sig figs. So this is 2016. So 2.016 grams of hydrogen, H2 per mole of hydrogen. And so what mass in grams has to react? Well, let's calculate that here. 71.9 kilojoules. 71.9 times 2 divided by 484 times 2.016. 0.2957 grams of hydrogen. I must have made a mistake earlier. Morning class. Well, in other words, 0.3 sig figs, 0.296. 296 grams of hydrogen. $65. The quicklime produced in question 63 is frequently converted to calcium hydroxide, sometimes called slate lime, by the exothermic reaction with water. Even here. So calcium oxide plus water. This is Lewis acid-base reaction producing calcium hydroxide. What mass in grams of quicklime was processed in the reaction that transferred 291 kilojoules of energy? So here, what mass of quicklime was processed? So quicklime is this. So it's 65.3 kilojoules for every mole of this. So we have 291 kilojoules, so we'll go from kilojoules to moles to grams. So note what they did here was they used positive 65.3. This would be exothermic, so it's actually negative 65.3, but this is produced. So I write the sign, I write produced here, otherwise it's a negative. So 291 kilojoules to moles, moles to grams. This is quicklime over here. This is slate lime, sorry, it's 1 to 1. So here, this is an exothermic reaction. So in the calculation itself, I'd say 75.8 plus 75.8 kilojoules of energy released for every mole of sulfur, for every 2 moles of carbon dioxide, for every mole of SO2, for every 2 moles of carbon. So when 10.1 grams of sulfur, okay, 10.1 grams of sulfur. So 10.1 grams of sulfur would go from grams of sulfur to moles of sulfur, and then from moles of sulfur to kilojoules. This many kilojoules for every 1 mole of sulfur. That should give it to us. $67. What mass in grams of octane component would you have to burn in your car? So again, this is going to be kilojoules. We're going to go kilojoules to moles. So we want to go from kilojoules to moles of octane. So when we look at this delta H, it's positive 1.09 times 10 to the 4 kilojoules released for every 2 moles of octane produced. And so that's going to be our conversion factor for every 2 moles of octane. And so we start off with 9.48 times 10 to the 5 kilojoules, that's what's given. And then for every 2 moles of octane, we get 1.09 times 10 to the 4 kilojoules, and then just go from moles to grams. Gives us grams of octane there. 68, the quantity of energy kilojoules transferred when 10.4 grams of carbon dioxide reacts with excess hydrogen. Delta H, this is endothermic. So we go 10.4 grams of carbon dioxide to moles of carbon dioxide. Moles of carbon dioxide to kilojoules. The ratio would be 41.2 kilojoules for every 1 mole of carbon dioxide. The moles of carbon dioxide, the grams of carbon dioxide. Just a standard energy stoichiometry problem. Okay, 69 are some definitions. Just look those up. Ideal, actual, percentage yield, limiting reactant, excess reactant. Heat of reaction, enthalpy of reaction. Heat of reaction and enthalpy of reaction are the same thing. It's just the energy involved in reaction. It's not that the reaction is the reactants are hot. You know, what happens is there's a transfer of potential energy to kinetic energy, which can make it hot. Joules, calories, stoichiometry, thermochemical stoichiometry. 70. Classify each of the following statements as true or false. Do this. True or false. '71 standard stoichiometry problem. 35 grams of nitrogen. You want to figure out how many grams of sodium carbonate. So 35 grams of nitrogen to moles of nitrogen to moles of sodium carbonate, moles of sodium carbonate, grams of sodium carbonate. We're done. This is just theoretical yield of this. This is a redox reaction here. It's kind of a complex one. Which is sodium carbonate, carbon, and nitrogen form sodium cyanide, carbon monoxide. Take a look at that. Grams to moles, moles to moles, moles to grams. Standard stoichiometry, grams of A, moles of A, moles of A to moles of B, moles of B to grams of B. What mass in grams of calcium phosphate will precipitate if excess calcium nitrate is added to a solution containing 3.98 grams of sodium phosphate? And so this is the same thing. We need a balanced chemical equation, which is shown here. And so it's a grams of A to moles of A, moles of A to moles of B, moles of B to grams of B. So it's just straightforward stoichiometry. Emergency oxygen mass contained potassium superoxide, KO2. What's the charge on potassium ions? Potassium ions are +1. Therefore, O2 must be -1. Oxygen is kind of interesting. We have O2 minus, this is oxide. We have O2 2 minus. O2 2 minus is called peroxide. And then we have O2 minus 1. O2 minus 1 is called superoxide. Superoxide is also an oxidizer, peroxide, but it can go either way. But typically it's known as an oxidizer. The superoxide occurs in the body, and its role in the body is as an oxidizer, so it causes oxidative damage to your body. But we can also use superoxide. Superoxide is in these self-contained breathing apparatus. So these self-contained breathing apparatus goes like this. Each time you exhale CO2, the CO2 reacts with the potassium superoxide and generates O2. And so what you can do is you can exchange CO2 for O2, so you can exhale and keep breathing. And it's a solid. You don't have to carry around an O2 tank, but you got to make sure you have enough. And so if we have 125 grams of potassium superoxide, how many grams of oxygen can be produced? So that's something you obviously want to know. You don't run out of oxygen. And so it's the standard. Grams of A to moles of A, moles of A to moles of B, moles of B to grams of B. We're done. Standard stoichiometry problem. Not limiting reagent because we don't need any of the others, or we have plenty of the others. Baking cakes and pastries involves citric acid and sodium bicarbonate. Here, we're given 6 grams of citric acid and 20 grams of sodium bicarbonate. And so when we look at this, this is a limiting reagent problem. How do we do a limiting reagent? Tell me, how do you do a limiting reagent problem? The smaller amount method. First, calculate the yield from First calculate the yield from A, citric acid. So the yield from citric acid is 7.87 grams. Oh, this is not the smaller amount method. What are they doing here? They're doing something called the comparison of moles method. I don't care which one you use. If you like comparison of moles, go ahead and use that. I like smaller amount. And so I wouldn't have done it like this. I would have done it, because I like to do it the same way. I'd calculate the yield from citric acid, then the yield of CO2. Then I calculate the yield of CO2 from sodium bicarbonate. What they did was they calculated how much sodium bicarbonate needed to react with all that citric acid. And they calculated 7.87 grams of sodium bicarbonate are needed, but they had 20 grams. So they have way more sodium bicarbonate than they need. And therefore the sodium bicarbonate is the excess. This is called the comparison of moles method. I would just solve it using the same method that I solve it each time. I like the repetition. This is why I like to convert it to moles. I don't like using kilomoles or that type of stuff. And excess. And so same thing. Citric acid. Can you name this? If you replace the sodiums with hydrogens, you get citric acid. Ic acid comes from what anion? Ic acid comes from 8. So this is sodium citrate. What's the name of that? Sodium citrate. Sodium citrate. Okay, I told you that there's one more section that we have to deal with in this particular chapter. And it wasn't discussed in the PowerPoints, but it is in the homework. So I'm going to talk about it now. And that deals with mixtures. So let's talk about mixtures. So reactant / product mixtures. Air is a classic example of a mixture, right? And so let's look at the combustion of methane. Methane plus 2O2 yields CO2 plus H2O. It makes a difference here what the states are. So let's plug them in. Like for example, H2O here is a liquid or gas? H2O here is actually going to be a liquid. If it were gas, it's going to change the amount of energy that's involved in this reaction. And so what I mean by mixture is this. Air is a mixture that contains oxygen. And so let's say I have 100 grams of air here. If I have 100 grams of air, is that 100 grams of oxygen? No, so what I have to do is I have to go from grams of air to grams of oxygen. Well, in order to do that, I need to know the percent composition by mass. So if I have 100 grams of air, how much of that is oxygen? Well, that we can figure out by just looking it up. Let me look it up. It's in one of these tabs, but I forgot which one. We have to be careful because when I look at this says that air is 20.95% oxygen. But that's not by mass. Do you know what this is by? This is by mole. This is what we call mole percent. That's not the percentage I want. I want a mass percent. And so I got to find the mass percent here. The mass percent, in the engineering toolbox, they call it weight percent. So if I look at the weight percent, it's right here. Do you see it? Air is 23.14% by mass. Oxygen. So air is 23.14% O2 by mass. And so what that means is I have 23.14 grams out of 100 grams. That's going to be 23.14 grams of what out of 100 grams of what? This is going to be 23.14 grams of oxygen for every 100 grams of air. And so if I have 100 grams of air here, I really only have 23.14 grams of oxygen. And so this is an example of a reactant mixture. And so I got to go from the mixture to the pure. Once I get pure oxygen, then I'll go to moles of oxygen, and then from moles of oxygen I can branch off either methane, CO2, or water. Likewise, I might be interested in how much air I need to combust. Let's say I'm going to combust 30 grams of methane. And so I have grams of methane, pure methane. I go from grams of methane to moles of methane. And then I want to figure out how much air I need. But I only have O2 here, I need 2 O2s. So I'll go from moles of methane to moles of O2. And then from moles of O2, I'll go to grams of pure O2. This is how many grams of pure oxygen I need. And then from grams of O2, I'll go to grams of air. Well, how do I go from grams of O2 to grams of air in the mixture? Well, I need the percent composition. That is, I'll have 100 grams of air for every 23.14 grams of oxygen. So grams of oxygen cancels grams of oxygen, using the grams of air. So this is how we deal with mixtures in the stoichiometry. And so this is the same type of problem here. A phosphate rock quarry can yield rock that is, rock is a mixture. It's a mixture of minerals, different minerals. Minerals are compounds. So it's a mixture of different compounds. That's what makes up the rock. And so a phosphate rock quarry yields rock that is 79.4% calcium phosphate. The raw material used in preparing calcium dihydrogen phosphate, a fertilizer known as superphosphate. The rock is made to react with sulfuric acid according to the equation. So calcium phosphate plus sulfuric acid yields calcium dihydrogen phosphate plus calcium sulfate. This is kind of a hybrid between metathesis and the Bronsted acid base. We don't have a complete reaction here of phosphate, phosphoric acid. What is the smallest possible mass of rock in kilograms that must be processed to yield 0.500 tons of fertilizer? Oops. This is, sorry. This is not a mixture. This is a different percentage. You know, what is this percentage here? This is not the percentage I just talked about. You know what this percentage is? Well, maybe it is the percentage I just talked about. So let's try to figure this out. Seems different, but maybe it's the same. So I'm going to have calcium phosphate plus 2H2SO4 yields calcium dihydrogen phosphate plus 2 calcium sulfate. And so I want 0.500 tons of fertilizer. The fertilizer is, what is the fertilizer? Calcium dihydrogen phosphate. So I want 0.500 tons of calcium dihydrogen phosphate. Dihydrogen phosphate is a -1 anion. And so what I can do is, I can do this. I can go from tons to pounds, 2,000 pounds of a ton. So tons to pounds, and then pounds to grams. So I get grams of pure calcium dihydrogen phosphate. And then grams of pure calcium dihydrogen phosphate to moles of pure calcium dihydrogen phosphate. And so I can figure out how many moles. And they want the rock. The rock contains calcium phosphate. And so what I'm going to do is I'm going to go from moles of calcium dihydrogen phosphate to moles of pure calcium phosphate. Moles of pure calcium phosphate to grams of pure calcium phosphate. But the rock doesn't consist of pure calcium phosphate. And so what is that percentage there? 79.4%. 79.4% means 7 by mass. By mass, it means 79.4 grams over 100 grams. And so 79.4 grams of what per 100 grams of what? Yeah, 79.4 grams of calcium phosphate per 100 grams of rock. And so I just need, this is your standard stoichiometry here. You know, it's grams of A to moles of A, moles of A to moles of B, moles of B to grams of pure B. But we aren't going to pure B, we're going to rock, which is a mixture of B. And so I need one more step here, and that is for every 100 grams of rock, it contains 79.4 grams of pure calcium phosphate. And so I need to tack on one extra conversion here to get the amount of rock I need. All right, so this is what they did here. They went from tons to pounds of fertilizer, pounds of fertilizer to grams of fertilizer, grams of fertilizer to, I hate this kilomole stuff. I would just go to moles of fertilizer to moles of calcium phosphate to grams of calcium phosphate, grams of calcium phosphate to grams of rock. And so here, if we stopped here, we get the grams of calcium phosphate, but we got to add one more step because we're not using pure calcium phosphate, we're using this mixture here. So we got to calculate the grams of mixture. That's exactly like this. We got to calculate how many grams of air we need, not of O2 we need, of air. Okay, let's take a look at number 78. Carborundum. Carborundum is silicon carbide. Silicon carbide is widely used as an abrasive in industrial grinding wheels. It is prepared by the reaction of sand or quartz, SiO2, or silicon dioxide or silicon peroxide, with the carbon in coke. So SiO2 sand plus carbon yields silicon carbide with carbon monoxide. What mass in kilograms of carborundum can be prepared from 727 kilograms of coke? That is 88.9% carbon. And so let's start off with the percentage first this time. We have coke. Coke is a mixture. And coke is 88.9 grams of what per 100 grams of what? 88.9 grams of carbon per 100 grams of coke. And so we got to figure out how we're going to do this now. In fact, we're starting off with 727 kilograms of coke. And so we could just do this, mapping it out here. Carbon, silicon carbide plus 2 carbon monoxide. So we don't have pure carbon, we have coke. And so we have 727 kilograms of coke. So I would do this, I'd go kilograms of coke to grams of coke. And then when we go to grams of coke, then we can use this relationship. You know, we can get grams of coke to cancel, and that gives us grams of carbon. So from grams of coke, which is a mixture, to grams of pure carbon. Once we're at grams of pure carbon, then we'll go to moles of pure carbon. And then from moles of pure carbon, we're going to carborundum, which is the silicon carbide. We'll go to moles of silicon carbide, to grams of silicon carbide, to kilograms of silicon carbide. So that should do it there. And so we're going to use this as is to convert from coke to carbon. Let's look at number 79. A sludge containing silver chloride is a waste product from making mirrors. The silver may be recovered by dissolving the silver chloride in a sodium cyanide solution and then reducing the silver with zinc. The overall equation is, so this is a combination of redox and Lewis acid base, actually. What minimum amount of sodium cyanide is needed to dissolve all the silver chloride from 40.1 kilograms of sludge? That is 23.1% by mass silver chloride. And so first let's deal with the sludge. The sludge is a mixture. And it's 23.1% AgCl by mass, or by weight. And so what does that mean? Well, that means 23.1 grams over 100 grams. And so 23.1 grams of what? Silver chloride. 100 grams of what? Sludge. Okay. And so this is what we do. We would go from 40.1 kilograms of sludge. Actually, I just write it here. I'm going to go from 40.1 kilograms of sludge to what? To me, I would just go from kilograms of sludge to grams of sludge. And then from grams of sludge to?
the silver chloride?
Yeah, okay, so I'd go from grams of sludge to grams of silver chloride using this conversion factor here. And so then I get grams of pure silver chloride. Once I have grams of pure silver chloride, that's going to take me into the stoichiometry map. And so how much sodium cyanide do I need? And so I'm going to go from grams of silver chloride to moles of silver chloride, and then moles of silver chloride to moles of sodium cyanide. And then from moles of sodium cyanide to grams of sodium cyanide, and then grams of sodium cyanide to kilograms of sodium cyanide. And so that should take me to where I need to be. Let's take a look at what they did here. So they went from kilograms of sludge. Now they use the percentage in terms of kilograms. You could use the percent by mass with any units. It could be pounds, it could be grams, it could be kilograms. So I'd like to be consistent. I like to be consistent because then there's repetition and more repetition, and it becomes more familiar. But here they just did 23.1 kilograms of silver chloride for 100 kilograms of sludge. And then they do this kilomole stuff. I'm not into this kilomole, kilogram stuff. So they do a little differently than I would do it. I just use a regular molar mass. I don't like too many units with different things. Anyway, pretty much the same. Let's look at number 80. Number 80, this is you know, the chemical equation that describes what happens in an automobile battery. So in an automobile battery, the oxidizer is lead-4 oxide, the reducer is lead. And we have an oxidizer reducer here, we need acid. And the acid is, the H plus is coming from H2SO4 here. So what fraction of lead in PbSO4 comes from PbO2, and what fraction comes? So the lead from the oxidizer ends up in PbSO4, and the lead from the reducer ends up in Pb. So 50% of the lead comes from the oxidizer, 50% of the lead comes from the reducer. Here. If the process uses 29.7 grams of PbSO4, what mass in grams? This is just straight stoichiometry. You know, I'd go 29.7 grams of PbSO4 to moles of PbSO4, moles of PbSO4 to moles of PbO2, and moles of PbO2 to grams of PbO2. So just a straightforward stoichiometry problem. That is. So it's not really advanced. 81. Hydrogen and chlorine are produced simultaneously in commercial quantities by the electrolysis of salt water. So if we take salt water and we generate an electric current through it, we can produce hydrogen and chlorine, sodium hydroxide too. Yield from the process 61% by mass. What mass of solution that is 9.6% by mass sodium chloride must be processed to obtain 105 kilograms of chlorine. Okay, before I do this one's complicated because there are two percentages in this problem. Since there are two percentages, we have to keep track of what each of those percentages mean. So before I do this one, I want to do another one that just deals with 1%. I skipped it earlier because I need to talk about that. So far what we've been doing is we've been using these percentages in stoichiometry. The percentages for the mixture. In this particular problem, we don't use the percentage, we have to derive the percentage. And so let's look at number 75. A laboratory test of 12.8 grams of aluminum ore yields 1.68 grams of aluminum. If the aluminum compound in the ore is aluminum oxide and it is converted to the pure metal by the reaction 2 aluminum oxides plus 3 carbons yields 4 aluminums plus 3 CO2s, what is the percentage of aluminum oxide in the ore? And so here we have to do a little bit of just algebra here to figure out, the percent aluminum oxide in ore. The percent aluminum oxide in ore is going to equal the grams. How many grams of aluminum oxide per 100 grams of ore? Times 100%. That's it. Are we starting off with 100 grams of ore? Actually, we are not really starting off. We're starting off with 12.8 grams of aluminum ore, not 100 grams. And so we're going to get a little less aluminum oxide. So what we can do is we can go, how many grams of aluminum oxide are there in 12.8 grams of ore? And then multiply this by 100%. And that'll give us the percent aluminum oxide by mass in the ore. And so the 12.8 grams of ore is a mixture. And so what I gotta figure out is how many grams of aluminum oxide are in that mixture. And I can do that based on stoichiometry here because they tell us something. They tell us that 1.68 grams of aluminum was produced in this reaction. Where did that aluminum come from? That aluminum came from the aluminum oxide. And so here I have my aluminum oxide plus 2 aluminum oxides plus 3 carbons yields 4 aluminums plus 3 CO2s. So what I'm going to do is I'm going to start here at 1.68 grams of aluminum and then go to moles of aluminum. And from moles of aluminum, I will go to moles of aluminum oxide. And from moles of aluminum oxide, I'm going to go to grams of aluminum oxide. And so this is just straight stoichiometry here. If we produce this amount of aluminum, all that aluminum came from aluminum oxide. Where did the aluminum oxide come from? The aluminum oxide came from the ore. And so we'll just plug that in here. So let's first figure out how many grams of aluminum oxide we had there to begin with. So if we produce 1.68 grams of aluminum, and all that aluminum came from aluminum oxide, then we'll go grams of aluminum to moles of aluminum. The moles of aluminum to moles of aluminum oxide using the balanced chemical equation, the moles of aluminum oxide to grams of aluminum oxide. And so if I form 1.68 grams of aluminum, assuming a 100% yield, that's 3.17 grams of aluminum oxide that must have reacted. And so I must have had 3.17 grams of aluminum oxide to produce 1.68 grams of aluminum. And that 3.17 grams of aluminum oxide came from the ore. And so this is equal to 3.17 grams of aluminum oxide per 12.8 grams of ore times 100%, which gives me this. It gives me 24.8% aluminum oxide. So 24.8 grams of aluminum oxide per 100 grams of ore, or 3.17 grams of aluminum oxide per 12.8. It's the same percentage, it's the same ratio. This is per 100 versus per 12.8. And so that's determining the percent composition by mass. This is determining the percent composition by mass. Now this problem is a challenging problem here, because this problem has two percentages that we have to keep track of. And so let's look at number 81 here, hydrogen and chlorine by electrolysis. All right, yield from the process is 61% by mass. What mass of solution that is 9.6% by mass of sodium chloride must be processed to obtain 105 kilograms of chlorine? All right, so what is the 61% by mass? 61% by mass is this. It's 61 grams per 100 grams. And so we have to figure out 61 grams of what per 100 grams of what. And so can you tell me it's going to be 61 grams of what per 100 grams of what? Now the clue is yield. This is a percent yield. If that's a percent yield, then it's 61 grams of product per 100 grams of product. In other words, what we're after is chlorine, and we're just about out of time here. And so let me tell you. It's going to be 61 grams of chlorine AY over 100 grams of chlorine TY. We're interested in the yield of chlorine, and it's a 61% yield. What is this 9.6% here? It's going to be 9.6 out of 100. And so that's going to be 9.6 grams out of 100 grams. And so what is it here? Yeah, 9.6 grams of sodium chloride per 100 grams of sodium what? So this is a totally different percentage. This is 9.6 grams of sodium chloride per 100 grams of sodium chloride solution or mixture. So for every 100 grams of sodium chloride mixture, I have 9.6 grams of pure sodium chloride. Or in other words, for every 100 grams of solution, it contains 9.6 grams of pure sodium chloride. This is like the ore that we were talking about earlier. And so this makes this problem pretty challenging because there are two percentages there that we have to keep track of. So we'll finish this problem next time.